Half-life is the time required for 1/2 of the radioactive nuclei in a sample to spontaneously decay. Okay, so if I start out with 4, I'm going to go down to 2. When I'm at 2, I'm going to go down to 1. When I'm at 1, I'm going to go down to 1/2. It's a half-life. Okay, half-life is specific to the type of radioactive material. So every element has their own half-life, and every half-life is different from element to element. The number of nuclei of the original radioisotope, so the parent element, remember if we look at the parent element, that's X, A over Z, left in a sample after a given amount of time can be calculated. So this is how we figure out the half-life. N is the amount of radioactive material remaining after a given period of time. So this is how much material is left. N0, which is N0, is the original amount of sample before decay. So it's the amount that you're starting with. Small letter n, because using 2 n's already isn't enough. N is the number of half-lives that occur over a given period of time. And it can be found by T being the time, and T to the 1/2 is the half-life of that element. Okay, this particular formula here is not on the data sheet. And so sometimes what you might see is you might see notation like this. Aren't? You want me to? Yeah, but it will have to come down. You can't have anything up. No, you're supposed to take it down. We looked into that because Mrs. Johnson thought that too for something, and we looked into it. Everything has to come down. Okay. The amount of a radioactive material may be expressed in different units. So you could have mass, you could have number of atoms, you could have percent, you could have decays per second. Becquerels is very common. It's the unit. Counts per minute, activity. But N and N0 have to be in the same unit. Okay? So even though we've not seen decays per second, we've not seen becquerels, we've not seen counts per minute, they're still a unit and they just have to match. Let's look at this. Exponential decay. When we look at exponential decay, time being measured in days, and activity counts per second. On the side, what we see is we start at some known amount. We start with some known amount, and if this is, let's just go 20, 40, 60, 80, 100, and over here, let's go 6, 8, no, 6, let's just change 6, 12, 18, 24 across. If I start out at 100, if I go to 6, I should be at 50. And if I go to 12, I would be at 30. And if I go to 18, I would be at 15, and so on and so forth. And so you see this, and we never actually do touch the x-axis. Okay? So when I look, half of 100 is 50. Half of 50 is 25. So that would have been here, 25. Half of 25 is 12.5, and so forth and so forth. We go down the line. Okay? We could also look at it at half-lives. And this would be percentage of original. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And 1 half-life, 2 half-lives, 3, 4. So if we started at 100, right here, in the first half-life, we would go to 50. 10, 20, 30, 40, 50. In the next half-life, we would go to 25. In the next half-life, we would go to 12.5. In the next half-life, we would go to 6.25. So on and so forth. Never actually touching that y-axis. Okay? So you've all seen an exponential graph. We've looked at exponential graphs in different purposes, and this is the purpose when we're looking at decay. So when we look at a problem, carbon-14 has a half-life of 5,730 years. How much carbon-14 will remain in a sample after 17,190 years if the original sample had 15.6 grams of carbon? So first things first, we're going to pick out our knowns. We know that the half-life of carbon-14 is 5,730 years. We know that the given time frame that we're looking at is 17,190 years. When we look at the original amount of carbon that we're starting with and not, it's 15.6 grams, and it's asking us how much is remaining afterwards. In order to find N naught, or N, it's N naught multiplied by a half to the power of N. That's the formula that we deal with. N is equal to NO times a half taken to some nth power. We don't have N. N is solved by T over T to the 1/2. Okay? So 17,190 years divided by 5,730 years. And for that, we get what value? 3. Okay? Then we can go back into our regular formula. We can go 15.6 grams multiplied by a half taken to the power of 3. And we get what value? Yep. Grams is the only unit that we have right now. Why would you want to? Kilograms are the base unit in physics, but in this particular equation, N and N naught can be any unit as long as they're the same unit. 1.95 grams of carbon-14 will remain. So does everybody understand how to go 1/2 to the power of 3? Do you know how to do that on your calculator? Okay. So this will be just a matter of being able to manipulate your calculator. Second question. Radium-226 has a half-life of 1600 years. What percentage of a sample of radium-226 will remain after 8,000 years? So, information that we have. Avery? Okay, so what letter is that in our formula? That is the half-life. It's telling us what the half-life time is. N is the number of half-lives. If it's telling us that it has a half-life of 1600 years, that's what T1/2 is. Okay. What's another piece of information, Cadence? Okay, what is 8,000 years? T. And Paulina, it's asking us to find what? It says what percentage of a sample of radium-226 will remain after 8,000 years? N. Capital N. Okay. So when we look at, it's actually asking us a percentage. So I'm going to do this instead. When we're looking at percentages, percentage is what's remaining over what we started with. Okay? It's asking us, these two values here come from N is equal to N naught times by half raised to some power of N. N we don't have. N is equal to T over T to the 1/2. Okay? So when we solve this, T is 8,000 years. That's what Cadence told us. And Avery told us the half-life is 1600 years. So how many half-lives does it go through? 5. Okay. When I come back to the formula, N is equal to N naught times a half to some power of N. When I look at this, n over n naught, which is just rearranging the formula, is equal to 1/2 to the power of 5. So n over n naught is equal to, what is 1/2 to the power of 5? Kylie, what would 1/2 to the power of 5 be? 0.03125. When I go back to percent, it's n over n naught. I forgot to add the times 100%. So n over n naught is 0.03125 multiplied by 100%. So we get 3.125% remaining. Okay. Questions? Comments? Concerns? Okay, I'm going to put these questions 2 to 5, 7 to 9, 11 to 14 up on the board because there's going to be another take-home assignment for this.